Okay, so I think we'll get started now. So first of all, thank you very much everyone for taking out time and coming to this exciting or hopefully exciting workshop about Intro to Deep Learning Frameworks. My name is Shyam Agarwal and I'm a second year computer science and engineering major at UC Davis. And I'm also a director of operations at GDSC this year. And just to let everybody know, all our events are open to everyone, and it's really great seeing new people in GDSC events and also our tech leads here. So let's get started about with regard to the workshop. And what a better way to start the workshop by saying that we'll not be using slides until very end, and we'll be using standard pen and paper strategy. So let me share my screen and get started. Just to confirm, you can see the screen, right?
Yes.
Okay, sounds good. Okay, so first of all, I want to make sure that we are all on the same page. And just to acknowledge, my handwriting is one of the worst in the world, but I hope it will make sense because I'll be speaking as I write. But as you know, this is an introductory workshop, which basically means that you do not need to know anything in particular to understand this session. But obviously, there are a few things that if you know, like some basic knowledge about coding in Python or some prior experience with basic machine learning models, it might help. But even if like I mentioned some complicated terminology, uh, don't get afraid. Like it doesn't have, it's just to give a better idea to people who might be aware of them, but you really don't need those things to understand the workshop. So let's quickly talk about what we'll be going through today. We'll talk about what these terms are, like what is TensorFlow, what is PyTorch, and some of you might have also heard of this thing called Keras. So we'll also see what Keras is. Then most of our time will actually be spent on understanding the theoretical aspects of like low level details about TensorFlow. Like basically we'll be talking about the TensorFlow ecosystem. We'll actually be building our own input data pipeline in Python. And then we'll be optimizing this pipeline by using prefetch and cache. We'll also be looking at TensorBoard, which is a great data visualization tool with your machine learning models. And this always will basically be done in TensorFlow. And we'll wrap up this session by having a quick contrast between TensorFlow and PyTorch. Also, if anyone has any questions, feel free to interrupt me and I'll be more than happy to answer them as we go. So yeah, let's get started. So the first question is, what do these terms really mean? Like what is TensorFlow, what is PyTorch, and like what is Keras? There is actually another framework called CNTK by Microsoft, but it's not that popular, so we are not talking about it. But TensorFlow and PyTorch are both open source, high performance libraries for numerical computation. An important point to note is that these are libraries meant to perform any numerical computation that you want to do. Basically, what I'm trying to say is that these are not libraries or like frameworks meant to do just machine learning or just deep learning. They are there so that you can perform any complex numerical heavy mathematical calculation. And as you might know, that deep learning often involves a lot of heavy mathematical stuff, and that is why we use them specifically for deep learning. But just so that we know, these are meant to perform any sort of numerical computation. I'm not writing these things up, but basically the idea of using this notebook is that I want to draw a few things while explaining and everything. But TensorFlow is by Google, PyTorch is by Meta's AI. Keras is actually not a fully fledged deep learning framework. It is just a wrapper around the three frameworks, which are TensorFlow. So this thing called, wait, why is my pen not working? Okay, sorry. Yeah, so Keras is just a wrapper around these three. Which three? TensorFlow, CNTK, and Theano. What I mean by wrapper is that earlier coding in TensorFlow was pretty difficult for people. So they made something called Keras, which was like an easier way to run your TensorFlow. Basically, when you used to use TensorFlow, you had to change your backend to Keras and you had to work on it. But Keras is not a fully fledged model. Like it's not an entire framework like TensorFlow and PyTorch. It was just supposed to be a wrapper. Now they have released a new version of TensorFlow called TensorFlow 2.0, which basically has this Keras thing inbuilt. So earlier you had to like specifically have Keras to run your TensorFlow stuff, like to make it easy and convenient for you to write it. But now inside TensorFlow, they have integrated Keras. So that is why when somebody says Keras, they're like, okay, we are talking about TensorFlow. But it's important to keep in mind, like when you talk to somebody and they're like, oh, what's Keras? So you know that Keras was something separate, and now it's a part of TensorFlow itself. Okay, so since now we understand what these three terms mean, we can look at some design overview of TensorFlow. Also, just to confirm, does anybody have any questions at this point? Okay, sounds good. So now we'll talk about the design overview.
Wait, hold on. So basically, like TensorFlow is like to do really complex computational stuff, and like what's Keras doing? Like it said it used to be separate, and now it's
So Keras was meant to be like Keras was built as a wrapper. So wrapper is something like instead of doing a is equal to 5, b is equal to 6, a plus b, you can just say that do an operation, which would mean the entire thing. It might not be the best example, but basically wrapper is something which helps
it,
you do something easily.
so it's like a function basically.
No, it's not really a function, but let me think of a good analogy. What I'm trying to basically say is that to do some operations, instead of like writing each and every operation and doing it, like it was getting difficult to do it in TensorFlow. So they came up with this wrapper, which was like, okay, you execute your Keras code, which will basically do all this TensorFlow stuff. But now TensorFlow has Keras as a part of it. So as we'll see, we'll talk about some API hierarchies in a few minutes, where you'll see that Keras is now a part of TensorFlow. And that's why we don't need to talk about Keras separately.
Oh yeah, it allows you to like name up, set names for like operations, right?
No, it's like that was just an analogy. It's
Oh
not
yeah, yeah.
the
It's
naming,
like it just
but
like it just like combines and operations into one.
you can think of it like that. It's not exactly like that, but if you like quickly do a Google search of like Keras code versus TensorFlow 2.0 code, like you can see the difference of
Oh,
like earlier they had to import Keras specifically, change the backend from TensorFlow to Keras so that they can run it. And now in TensorFlow, they are like, okay, I want to use tf.keras, which is one of their
okay,
APIs. And I think it would make a little more sense as we proceed.
okay, that makes sense.
Got it. So now we'll talk about some design overview. And as I said, TensorFlow can be used to solve any numerical computation. So if you want to solve like partial differential equations in physics or something, it's great for that. Now it's getting extremely popular because you can write the code to perform the operation in a high level language like Python, and it can be executed in a very fast way at the runtime. So what I'm saying is that you can write your code just like in your high level languages like Python, because it's a library for Python, supports other languages as well. And that gets run in a very fast way. The question now is, why is this computation so fast? And for that, we are going to look at this design overview so that we can actually see like what TensorFlow is doing inside. So TensorFlow has this thing called DAG. DAG stands for Directed Acyclic Graphs, or rather, I would say directed acyclic computation graphs. So what TensorFlow basically does is it represents its operations as a graph. And we know graph is a pair of vertices and edges, right? So for example, this is a graph. And since graph has these vertices or nodes and these edges, a question that would arise is like, okay, I have a graph, but what are these nodes? What are these edges? So in my DAGs, or these directed acyclic graphs, these are computation graphs. TensorFlow represents its operations as these graphs, where my nodes represent the mathematical operations and my edges represent some data. Over here, I actually ended up making a cyclic graph because this is a cycle, the entire thing. So I'll just remove that. But the nodes in my DAGs are operations, my edges are data. So for example, this can be the addition operation, this can be a subtraction operation, and these edges are representing data. Data is flowing between these nodes. Okay, so I'm trying to like give a hint of something. We call this framework as TensorFlow. And I just mentioned that these graphs, nodes are operations and edges have data flowing through it. Does does somebody see a connection like TensorFlow, data flowing? Does that give you an idea of what we are going towards? Like does that give you an idea of what tensor probably means? Or is it something I'm just making up? Anybody wants to volunteer? So I'm saying that this framework is called TensorFlow and the graphs have data which is flowing. So can you see like what tensor might mean? Yes, exactly. It has to do with data. So let's actually talk about what a tensor is, right? So tensor is nothing. We know what scalars are, right? A scalar is a rank 0 tensor. After scalars, we know what vectors are, right? So in physics, like vector is something with magnitude and direction and like in general, but in computer science language, when we say vector, we mean a one-dimensional array. So this one-dimensional array is a rank 1 tensor. And as you might guess, following it is a two-dimensional array, which is a rank 2 tensor. Then we can have three-dimensional arrays, which are rank 3 tensors, and so on. So we now basically know that tensor is n-dimensional array. So now it might make more sense when I'm saying that this node represents some operation. These edges represent flow of data, flow of data, flow of huge amounts of data, flow of arrays of data, flow of tensors. So that is why this framework is called TensorFlow. Does that make sense?
Oh yeah, so wait, you said it's like the data flows through the operation, like
Yes,
it goes from one operation and then goes to another operation and so on.
exactly, Aaron.
Uh-huh.
So that's why we call this TensorFlow. So since I said computation is a data flow graph, and obviously this is not a good depiction on my end, let's actually talk about how would you represent a neural network as a computation graph. So if you don't know what neural networks are basically, these are called neurons. Let's say this is my input layer. I have this hidden layer. I have this output layer. I might be using some terminology that you're not sure of, but you basically don't need to like know this to really understand what I'm trying to convey. And that's why I'm like quickly going through this. But basically in neural networks, you have all of these connected. Each edge over here is representing some weights. So when you do computation, you have something like each of the parameters multiplied with the weights, and then you add something called a bias in the end for reasons discussed later on. But what I'm trying to say is, if you want to represent this neural network as a computation graph, this is how you can do it. So here is my tensor. I have some data. Sorry, I meant to write I have some biases. This B thing is called bias. I have some weights. I have some matrix examples, and I would have my labels. So first thing is, I want to multiply my weights with my examples, right? I want to multiply my weights with my examples. And if you look into some linear algebra, you can represent this multiplication as a product of two matrices. So that's why what I do is I say, okay, I have my tensor, multiply them, do matrix multiplication. So this data comes here, this data comes here, and the output is this thing. Now I know I have my bias and I want to add it. So I say, okay, get my bias and let me add it. Okay. Now what I do is I pass this data through a non-linearity function. If you know what it is, sounds good. Otherwise, the basic idea is basically that you are putting in your data and you're asking it to operate on that data. And then probably you can have like some cost function, like finding your error, basically mean square error or whatever way you're doing it. But the general idea over here is that each of these nodes are representing a mathematical operation, and this is how you pass your data into this. Okay, so I think now we have some understanding of what is happening inside that. You make these this, you represent your computation as a data flow graph. Now obviously
Yeah,
the,
so like you said, tensors were like were like arrays, right? So like the data will pass through the arrays and be put into the operation, right?
yeah, so basically you just don't have, when I say array of data, I'm trying to say that you have a lot of data.
Oh,
So now, since you know that this is how things are working, another obvious question that rises is, what's the benefit of having these computation graphs? Like, how in this world are they helping me? So the first reason is, can somebody tell me which language I wrote this computation graph is? Is this Python, or is this C++, C sharp, or is this Java, or is it some other language? Can somebody tell me? What I'm trying to ask is, what language am I writing this graph in? Yes, Alan, exactly. Uh, no, there's no language involved, right? I never talked about any language. It's a language independent representation of my operations. So that is the first reason why you want to use DAGs, because it does not depend on what language you're writing it. So basically you can build this thing in Python, store it somewhere, reuse it in some other language like C++. If you want to do that, that works in TensorFlow, which basically means that it has software portability, does not depend on what software, like what coding language you're using. Secondly, it can run on CPUs, it can run on GPUs, and it can also run on TPUs. So does anybody know what TPUs are? Anyone? Okay, so yes, exactly, Georgie. So TPUs stand for tensor processing units, and these are like AI accelerator application specific integrated circuits, which basically means that these are circuits specially meant for your AI stuff. But this, what I'm trying to convey over here is that since these can run on any of these devices, there is also hardware portability. So basically, it's similar to the idea of having Java virtual machines. Like, what Java does is they compile their code into special bytecode, and that same bytecode can be run on different machines based on what Java virtual machine they are using. Similarly, what here we are doing is, this graph can be used on any hardware, any software. There is something called TensorFlow execution engine, which takes care of like mapping it based on your particular hardware and everything. So what I'm trying to basically convey is that it gives you a lot of portability. Now Also, there is something called TensorFlow Lite, so you can actually like train your models on like full computation power on cloud and literally run your machine learning models on your phone. So even in like very less computing power, like the power given in your phones, you can run these models because they are stored. Like you can store them and run them later on. Okay, so that kind of makes sense to us. Now, another point of interest is that what TensorFlow does is, since I was giving that example where I was like making some data and whatever be it here, and then I have some operations, we know that some operations are faster when you run them on GPUs compared to when you run them on CPUs. So what you can do is you can actually say that, hey, run this operation, just these operations on GPU, because I know that multiplication, matrix multiplication takes happens faster in GPUs. And then I can be like, do the rest of the stuff on CPUs. So if you see, not only can you have like different hardwares, but you can also have like, okay, run this part over here, run this part over here. And actually you don't need to worry a lot about this because TensorFlow automatically is able to decide, okay, I can run these things parallelly, I can do this on my own. And also obviously when you have like multiple devices, you would want them to communicate with each other. Like your CPU wants to communicate with your GPU. So TensorFlow takes care of that with help of something called send receive nodes, etc. So basically, it saves us from like thinking a lot about these things because it does it on its own. And there are like other things like it has specialized optimizations for linear algebra operations. It has automatic differentiation. All those things like we don't have to worry a lot. I just want to quickly introduce this idea of single process configuration versus distributed process configuration. And what this idea is about is that in single process configuration, when you have your process, right, like you have some client, some master, basically the work is given to just one worker in your single process configuration. But in distributed process configuration, the work can be divided into multiple workers. So again, this is beneficial because it adds to the parallelism thing, and like your operations can run faster. Like we don't need to go into details of like understanding these things, but it really helps in appreciating this framework and like why it's getting so popular. Also,
Oh yeah,
I
so the thing says like what does that say? That's a process, the mental what the that one, the thing below client, yeah.
yeah, so basically what I'm saying is that in single process, your master just tells one worker to do the work. But in distributed process, you can ask like multiple workers to do the work. So that
Oh,
helps.
okay, that makes sense.
Yep. Also, in the end, I just want to like quickly talk about what API level hierarchy is in TensorFlow. And that would finish our talking about the design overview and the ecosystem. And then we can actually build our input data pipeline and go on coding and everything. So TensorFlow has this thing called API hierarchy. And the base of this hierarchy is, as we discussed, CPU, GPU, TPU, like your code can run on any of these hardware platforms. Actually, it can also run on embedded systems. So if you're doing a project in Raspberry Pi and you want to use TensorFlow, you can still use it because it can run on your small chips as well, basically. Then the next level is core TensorFlow, C++. It's like very low level in the sense that if you want to like define your own operations in TensorFlow, you can define them in C++ and then register them as a TensorFlow operation later on. Then they have a core TensorFlow in Python, and it gives you like all the control. You want to do addition, subtraction, any complex mathematical functions like softmax or matrix multiplication, or like whatever you want to do, you can do them using this level of API. Then comes something which you might use a lot, which is called tf.losses, tf.metrics, and tf.optimizers. So as we'll see, like in machine learning, there is something, these are called optimizers, which basically optimize your cost function and all. So if you're using something like stochastic gradient descent, like I'm just throwing these names off so that if you later on encounter these things or you already know about these things, you can create a link of why TensorFlow is important. And you might feel like we are going over unnecessary stuff, but trust me, it's important to have a general idea so that we can appreciate the framework in which we are working. And we're just not saying that this works faster, but we actually know why it works faster and like what all features it implements. So basically, if you want to have any optimizer like stochastic gradient descent or Adam optimizer or whatever, you can like directly use it from here. So basically, you can build your custom machine learning models because you are given the respective components using tf.losses for loss functions, tf.metrics for calculating metrics, and so on. And the topmost highest level API is tf.keras, tf.estimator, tf.data. And actually, we'll be looking at tf.data when we are building our input data pipeline. But basically, the idea is that you might not want to create your own machine learning models, right? You might just want to use whatever is already there. So you can use one of these over there. And that's what I was mentioning in the beginning, that now they have made Keras as a part of the hierarchy itself. But that basically kinds of gives us an overview of, okay, what this TensorFlow thing is and like what it's doing internally. Just to confirm, how is everybody feeling about this? Did it make some sense? Okay, seems like it makes sense. Okay, so if it does make sense, let's talk about input data pipeline. And this is kind of like a fancy name, but all it means is processing my data before I can pass it to my machine learning model. So what happens is you have your data and you want to give it to the machine to train on, like learn something from it, predict something from it, classification, regression, whatever sort of problem you're performing. But in the process, you would want to process your data because, for example, if you're doing some NLP task, you might want to remove stop words because they are not important for your operation. Or stop words are words like uh, and, or, not, things like that, basically, which don't give that value. It might give value depending on your operation. But what I'm trying to say is all input data pipeline does is it means pre-processing my data so that I can convert my raw data into a stage where it is ready to be given to the machine learning model. So let's, since we're talking about,
so the input data pipeline line like formats the raw data into something that like the machine learning can deal with.
yeah, something which we can feed into our machine, and we'll actually be building the pipeline, so you'll see what the process looks like. So yeah, so let's talk about a problem at hand. Let's say I have a few images with me. These are images of cats and dogs, and I want my machine to predict whether it is a cat or whether it is a dog. Okay, so that's the problem at hand. Now, assuming that we are doing something significant and like we have a huge data set, I'm assuming I have 2 million images with me. So this is 2 million images, and each image is probably 10 kilobytes. If it's 10 KB, sorry, it's, yeah, so if it's 10 KB, then I have basically 10 to the power minus 6 times 10 GBs, right? This is the amount of memory I would need to store these 2 million images. See, if we had like 100 images, you can load that 100 images into your RAM. But if I look at this is 20 GBs of RAM. And is anybody over here having 20 GBs of RAM in their system? Because I don't. And I mean, you can have 20 GBs of RAM, but oh, okay, David has 32. Pretty nice. But I mean, as we know, somebody has 64 GB RAM. Wait, I'm talking about RAM, which is random access memory, not the hard disk storage. But if you have, that's great. But we usually like don't have that much amount of space in our RAM, right? We also have other operations to run and so many other things to do. So what we can do over here is, how about, like, can somebody suggest what we can do if we have like 2 million images? We cannot load everything all together into our RAM. So how will we like train it? How will we give it to my machine learning model? Any suggestions on what we can do? Anyone? Oh, somebody said random sampling. Uh, okay, I mean, maybe that's a valid way, but then that basically means that there's no point in having so much huge amounts of data, right? Because you'll just taking a small amount. What we can do instead is, why not I take batches of data? Why not I take just 1,000 images, train on it, next 1,000 images, train on it, and keep on doing it. So maybe I can have a very specialized data structure, and what this data structure does is it gets data in batches, performs all my operations, and again gets data in batch, perform operation, gets the next batch, performs operation, and keeps on doing that. I actually did mention in the earlier what this data structure is called. Can somebody tell me what this data structure is?
Oh wait, so like you do the thing where you just send 1,000 images at a time?
Yeah, so basically, since you cannot load all the 2 million images, the option is that, okay, let me load few images, train, few images, train, few images, and train. So that's
Oh,
what data structure
is
is.
that what you call pre-processing or not?
No, pre-processing basically means, so this process of like getting things in batches and doing it, it's called streaming. But pre-processing means processing data. So processing
Oh.
data can be like, if these are images, I might want to filter them based on they're blurred or not, they're not blurred, or maybe I want to unblur the images, or once you have their pixel values, you might want to scale them, and we'll actually be doing scaling and everything. So you'll see there also what processing means.
Oh yes, streaming is a thing where you add only a little bit at a time, and the data structure down there is the thing that's doing the pre-processing, right?
Yes, but can somebody tell me what this data structure is called? I did mention it. Okay, let me go back to the page where I mentioned it. Oh, I did mention it here. I did say that we are going to deal with this thing. Okay, so if you don't recognize this tf.data, so we are going to use something called tf.data.dataset. So tf.data is the high level API, and we are using tf.data.dataset to basically perform this operation. So what we are doing is, let me now share the code file and show you how this works. So what I am using is, I'm using something called Google Colab. It's just like Jupyter notebooks if you have used them, and we are Google Developer Student Club. We highly support Google technologies, but we are not biased towards other technologies. But yeah, what I'm trying to say is that, let me reconnect. So I'm using this notebook because I didn't want to like install everything on my own devices, and like if you want to like run it, you can just run it on cloud basically. So this is what I'm doing. Also for citations, this code is taken from Code Basics, and I did do some slight modifications based on what we want to cover, etc. But I'll quickly go through what these are doing. And honestly, if you have doubts in like what a function does, it's always a good habit to go online, search about it, read through the documentation of what those functions are doing. But honestly, as we know, Python is a pretty easy language to learn, and that's why it's usually the first language people learn or something. But like, it will make sense. These names would make sense of what we are doing. Firstly, what I'm doing is I'm importing my drive because my drive has some data which I need to use. My Google Drive has some data. I'm importing TensorFlow as TF, which basically means, hey, from now on, I will call TensorFlow as TF. I have this array of data, And what I'm doing is I'm loading this data into my data set. So basically, when I say for each of these variables, which I'm calling as sales, print sales.numpy, you see I'm getting all my data. So basically, I was storing this data in tf.data.dataset. Or what I can do is I can also say that for each of them as numpy iterators, you print them. Numpy is another library, and like it's just that each of these are objects and I want to see them. So I'm saying print them after converting it to numpy. Now, if I just want to like get 3 things from my data set, like just the top 3, I can be like, okay, dot take 3. And we'll actually see this dot take is important when we are training, like when we are preparing data for training, and we'll see it later. Then there is something called lambda function. Honestly, I'm just like showing these things so that you have an understanding of what pre-processing might mean. Like obviously it's pretty basic. These are numbers, you're just manipulating, adding something. But if you compare, the analogy is really good. I had a bunch of numbers. Maybe I didn't want the negative numbers for whatever reason it is. And I can be like, okay, when I'm pre-processing my data, I want to remove the negative numbers. So over here, I have this lambda function. What it basically means is for each of the datas, call them x and filter it out if x is greater than 0. So over here, you all only get the positive values. I can run and show. Then maybe these represented some currency values. So maybe these were US dollars. These values were US dollars, and I wanted to convert them into Indian rupees. And assuming the conversion rate is 83 or something, I can just quickly multiply them and I see them in the Indian rupee value. Maybe I want to shuffle my data
Hold
because
on, what was that data structure called again? You said it was like the data structure that
yeah,
pre-process the data is just like the TensorFlow functions, right?
this is it. tf.data.dataset.
Oh yeah.
So I can also shuffle my data. And if you want to actually know what this parameter 2 is and like how it shuffles, it's this Stack Overflow thing is pretty nice. Over here, they tell you that buffer is basically the size they get values and take one value, keep on doing to get the shuffled value. But you can look at it if you want. The link is here. Then if I want to do batching, I can say dot batch. So pretty much like it's pretty easy. These names are pretty easy. Like what do I do for batching? Dot batch. What do I do for shuffling? Dot shuffle. What do I do to take some values? Dot take. So if I said dot batch 2, like you see, it made batches of 2. If I maybe want to have batches of size 3, I have this. I'll quickly go back, do it to batches of size 2. Now, the beauty of TensorFlow, like obviously the main reasoning why we did the entire ecosystem thing was to understand why all these things are happening very fast. And obviously the data that we have right now is like very low scale, so you might not appreciate it that much. But another important thing is that the entire code that I wrote from here to this entire thing can just be summed up in this single line, which is pretty nice because you won't, I don't think you would like to write so many lines of code. You can just be like, okay, from my data set, filter the values that are positive. Dot map basically means that apply this everywhere, multiply into 83, each of those values, you shuffle them and you batch them. And if I run this, I get the exact same result. Okay, so that was like a dummy data set. And now I actually run the cat and dog example that we did. So basically, what's the question at hand? I have images of cats and dogs. I want to do some processing on data on those images so that these images are ready to be given to my machine learning model. So this might be of interest to people who are also like looking into data analysis kind of thing. Like, okay, you can use this to uh, engineer your data basically before giving it to the machine learning model. But on my drive, I have an images folder, which basically have a lot of images over there. I have that on my drive, and that is why I mounted my drive in the beginning. I'm seeing over here the length of my data structure. So, okay, I have 130 images. What is the type of this? This is a tensor slice data set. We don't have to worry about it. I'm just showing you that, like, if you'll go through the documentation, they'll mention a lot of other things as well. So now currently what I've done is I'm creating a data set. I am having this data structure tf.data.dataset which basically has the address of my files. It does not have the files, it has the address of the files. So if I basically print, if you see, this is the address. So in my drive, I have something called a folder called my drive, which has images, which has a folder called cat, and this is the name of the image. Similarly, if I want to like shuffle, as I did earlier, I can shuffle, and if I choose 3, you will see that I get like some random 3 values. So, okay, I have my data. I also have some labels, right? Like each image is either a cat or a dog. So I tell it that, okay, my class names are cat and dog. So since we are pre-processing this data, I had like bunch of data. I went online, did some web scraping, and I got bunch of data. Let's say this is what the scenario is. Because I want to pass it to the machine learning model, I actually need to first map each image. Like, okay, I need to know that this is a cat image, this is a dog image, right? Which was basically stored in this address. So in this pre-processing operation, my task is to get each image and its label so that I can give it to the machine later on. Does that make sense? Currently, I have like bunch of images, but now what I'm doing is I want to have a structured thing in the code where I have each image corresponding to, like, I know this is image, this is a cat, this is image, this is a dog, so that I can give it to my model and like train it, test it, everything. Okay, so over here, since I had like 130 images, I'm saying that, okay, I will use 80% of that data to train my machine, and I will use 20% of that data to test how it's performing. So I said this is my train size, and I just take the 80% values into my train data structure, and skip is just doing the opposite of take. So it has the rest of it for testing. If you check, it's 80%. I mean, obviously approximately, if I'm not wrong, but yeah, it's 80% values are training, and 26 values are for your testing. Now what this get label is doing is it's basically getting the string, the address, and this path dot separation is basically, since this is a MacBook which I'm using, this is the separation thing in MacBook. This, if you are a Windows user, the separation would probably be this. So what it is doing is it's just saying that, okay, whatever the string you give me, separate it based on the separation thing. If you do this, you get your label over here. And then I'm creating a function called process image, which basically says, hey, this is my label, like get the label from the file path, which basically means get this label. So what I was doing is I was like saying, give me parts minus 2. So parts minus 2 would basically mean this is read from the right side. So this is -1, this is part -2, because you were splitting everything based on this os dot path dot separation. And if you feel like I'm going really fast with this code, do let me know. I'll calm down. Otherwise, if you'll go to the notebook again, I'm pretty sure things would make sense. So over here I'm saying, okay, give me the label, and I actually read the image now. So till now everything was happening with the address, but now I say, go get that image. And then there is this function called decode jpeg, which basically means decode my image. So each image can be represented as a bunch of pixels. So these are like your pixels. So these represent RGB values, like how red, green, like basically RGB values. Like if you have a bunch of RGB values for each pixel, you can create your image basically. So that's what this is doing. And then I resize it to 128 by 128 because each of my picture can be of different dimensions, and I don't want that to happen because I don't want to give like different dimensional data to my model to train it. Okay, so once I do this, uh, I just ran it so that you can see that this is how each decoded image looks like. Now, again, I say map, which basically means on each of my elements, perform this operation. On each of my elements, perform this operation. So, okay, so I think I got an error. Oh, probably because I forgot to run this piece of code. Let me quickly run this. It takes one positional argument, but two were given. Let's see why this happened. Process image. Oh, okay. I think I know why this happened. This probably happened because I ran this notebook right before the session started to make sure everything is working fine. And like I'll have to like restart the notebook and like run everything from the beginning probably. But trust me, these are like most likely that's why it's happening, because all these instructions have already been run. But whatever output you're seeing over here, this is the correct output. So I think that's the reason. But what I'm doing over here is basically I'm now since for each file I know what the image is now, I also know what the label is. I finally have each image and my label over here. So basically we started with a bunch of random images and we finished with my image. Like I'm just showing a few entries of this image because it's 128 by 128, the entire thing. But now we literally have this image and we also have its label. We have the image, we have its label. We have the image, we have its label. So this basically finishes creating our input data pipeline. Our input data pipeline is ready for us to use now. Is everybody clear with what we mean by creating an input data pipeline? You started with some raw data. Now you have structured data basically, where you did some mappings, you shuffled your data, you scaled the data, and now it's ready to be given to your machine learning model. Does that make sense to everyone? Does anyone have any questions? Okay, sounds good. So now I do have just so now I have like just 5 minutes of theory so that we can know what prefetch and cache are, and then we'll look at TensorBoard and we'll contrast the two frameworks and we'll be done. So let me again share my notebook with you all, then do the shared content screen. And can you see my screen?
Yes.
Okay, sounds good. Just give me a second. Zoom up. Wait. Okay, yeah. There we go. Okay, so what we currently saw was, just give me a second. Okay, everybody can see my screen, right? There was some technical glitch. Okay, sounds good. So what we just saw was we had this data set. It can be anything. Currently, we had it on our drive. It can be on your S3, Amazon S3 cluster. It can be it can be anywhere, whatever data set you have. We performed some basic operations, like we loaded in batches, we shuffled data, we mapped data, we filtered data. And actually, if you hear somebody saying ETL cycles, that's what they mean. ETL, extract, transform, and load my data. So you extract data, transform it, and you load it. And then it's ready to be given to your model over here. Okay, so we are clear with that. Now, what
Yeah,
I want.
so the thing that thing is the thing that processes the pre-processes the data set and stuff.
Mhm.
Yeah, hold on. Is that like batch, shuffle, and fill? Yeah.
Yeah, so if you remember, we had this function where we were shuffling our data. We did dot shuffle. We also batched data. We said dot batch. And we also used map function a lot of times. So basically, like what I'm saying is this entire cycle is called ETL cycle. So like you might hear a lot of times that like people usually say that, oh, this is data from ETL cycle, which basically means the data was extracted, transformed, and already loaded, and now here we are like with that data thing.
That makes sense. Thank you.
Got it. Okay, so now since we were talking about that CPU GPU thing in the beginning, what I'm trying to what we are doing is, if you remember, I'm reading something from my CPU and I'm training my data, right? Since it's like 20 GBs of, it was taking 20 GBs of RAM, we said, okay, let's load in batches. And that's what we called streaming, right? So let's say I have like 3 batches. To load a batch, loading happens with CPU. To load a batch, it takes 3 seconds. To train a batch, we are training on GPUs. GPUs are usually faster for training, but there are a lot of things over there. But for GPU, let's say the training happens in 2 seconds. Since we are like having this loading, training so many times, isn't it taking a lot of time? Like I first load, like you said, load batch or read batch, whatever you say. So I read batch number 1, I train batch number 1. I read batch number 2, I train batch number 2. I read batch number 3, I train batch number 3. Can somebody tell me how long this entire thing takes place? Like if I have 3 batches, reading takes 3 seconds, training takes 2 seconds. How long will it take for the entire thing to happen? Anyone? Yeah, exactly. It will take 15 seconds, right? Because 3 seconds here, 2 seconds here, 3 seconds here, 2 seconds here, 3 seconds here, 2 seconds here. Isn't that a lot of time though? Like we had like 2 million data, like obviously like 3 seconds, 2 seconds is too much to load and train, probably also depends on the things. But since we are doing this multiple times, is there a way we can improve this? Yes, indeed, there is a way. Because if you look over here, this time, what is my CPU doing? It's just lying vacant, right? Over here, my GPU is lying vacant. Over here, my CPU is lying vacant. Like it's sitting idle. It's not doing anything. Why would I want my machine to do nothing, right? I would want it to do something. So instead, how about this? You load, you read batch 1, you read batch 2, you read batch 3. As soon as you read batch 1, you tell your GPU, hey GPU, start training. So this training will finish in 2 seconds. But as soon as you finish reading batch 1, you also tell CPU, don't wait for GPU to complete the training. Go ahead and start loading the second batch. So basically you're kind of being like a strict person, and you're telling these hardware things to work like this. So you're telling, as soon as you read, GPU start training, CPU start reading the second batch. Now obviously GPU is done here. GPU cannot do anything here because it doesn't have the data. CPU is still reading it. But as soon as CPU finishes reading the second data, you are like, CPU, come on, go read third batch. And you say, GPU, come on, go train the second batch. And then as soon as this happens, you train your third batch. Now how much time will it take? Can somebody tell me? So earlier it was taking like 15 seconds, right? But now if I do this, ensure this thing is happening, how much time am I saving basically? Yeah, it's taking 11 seconds, because 3 seconds here, 3 seconds here, 3 seconds here. Like this happens 3 seconds, this happens 3 seconds, this happens 3 seconds, and then this happens only 2 seconds. So 3, 6, 9 plus 2, 11. So this entire thing takes 11 seconds, and thus I save 4 seconds of my valuable time. Okay, so that is the one idea. And TensorFlow has something called prefetch, and it has this argument called auto tune, which basically says, TensorFlow, you decide how many batches you want to load after something like, don't ask me how many to do, you decide on your own. So this thing would convert this thing to this. Also, second thing is cache. You might also have heard about what caches are. So what we are doing here is, usually when you train your data, you don't train your data just once. You pass the entire data set to the machine to train it multiple times. And there is this term called epochs, which basically means number of times I'm training this data set, which basically means that, like, not training actually, yeah, kind of. So basically the number of times you're passing your data set to the machine. So you have this file with your images, you train the entire thing, but you just don't train it once, you train it multiple times. So you had 1,000 images, you give it to the machine again. You, like in our example, we had 2 million images, right? So you train on those 2 million images multiple times. So you train it on once, that's first epoch. You train it again, it's second epoch, and so on. So now if you realize, what would happen is, since we already made our input data pipeline, I know what we had to do. We had to open the file, we had to read the file, we had to do some mapping and like other operations basically. Then you pass it into your model to train it, right? So what is happening is, it will take some time to open it, it will take some time to read it, it will take some time to perform all these operations, and it will take some time to train it. Then again you repeat this operation: open, read, map, train, open, read, map, train. Now the idea with cache is that, also just to mention this, you don't need to open it again because the file is already open, so you can continue reading it. But um, after your epoch finishes, like the entire thing, then you again load your file and repeat the process. Now the idea with cache is that I already know that opening, reading, mapping, this entire three things would give the same result, right? Like the data that I have after these three operations, I want to just use that. So when you use this idea of caches, what happens is, again, you had open, read, map, and other functions, and then you had your training. So now you say, okay, open my file, read it, do all the operations, whatever time it takes, and train it. And then you again say, read, all, do all the operations, train it, and you keep on doing this. But in the second epoch, like once the entire thing happens, all the data has been passed, you don't need to do any of these, because with the help of caches, you're able to reference basically what was here, like after performing these three operations. So now on, your epochs would be pretty small because all you have to do is like train on them. So now what we are going to see with the help of code is that how this uh using the cache thing and how prefetch saves us time. And thus we'll open our second Google Colab notebook.
So the catch thing, it just like does the operation. Could you do the operation beforehand?
No, so yeah, so what cache is doing is, since you know that you will be loading, opening the same file, reading it, mapping it, the same file multiple times, what cache is saying is, you know what, I know what the result would be after these three operations. So in the first epoch, like the first time when you're passing everything into your machine learning model, okay, in the first time you keep a track, like you make them. But second epoch onwards, you don't need to again open, read, and perform all these operations. From them, there you already have it basically. So
Oh,
that's,
so it keeps the file, the thing the data set open, right? And something.
so no, so the idea was basically that the thing was already open, the file was open, and you were like reading, mapping, training, reading, mapping, training, you would keep on doing that. In the second epoch, you were again opening, reading, mapping, training, reading, mapping, training. Like each epoch you open your file once only, but you read, map, and train, because these are like different images. I think, let me actually go ahead and share my screen again and try to explain once again. uh, Over here, share screen. Okay, how do others feel about this idea? Does prefetch make sense to everyone? That idea of asking CPU to work alongside. Anybody? Anything to share? Okay, sounds good. So what I was trying to say over here, Alan, is that if you look at this thing, in my first epoch, let's say I had 2 million images and I do 1 million images once, and my second batch was 1 million images. Okay, so I'm just having like 2 batches. So this is what I open the file. I do this on the first batch and I do this on the second batch. Now what I will do is I will again open the same file, do this first batch and do that second batch. So each epoch I open file once only. But the point is that when you are doing these operations from the second epoch onwards, we are telling the machine that, hey, keep a track of what had been what was the result of operations up until mapping. And so basically now on what will happen is you'll just have to put it in the training, like spend time in training and not spend time in doing all this stuff.
Oh, so it keeps track of what has already been read and mapped, right?
Yeah, so technically, like what this idea of cache is that you already did that operation, so now you can reference to that. I mean, it's not exactly, I don't know exactly how the hardware does this thing, but that's like the high level idea of what cache is do.
Uh-huh.
Like maybe internally it keeps a track, or maybe internally it stores it somewhere. Like I'm not exactly sure, but yeah. So let me, where is my code file? Just give me a second. Let me open my code file. Okay, everybody can see my screen, right? So we'll not go into this code in that detail, but just to show you what we are doing over here is we are saying that import TensorFlow as STF, import time, because we want to keep a track of time. We're just seeing what the version is. We are actually trying to simulate what was happening there. Since we don't have that huge data sets, we cannot load that many things and like actually do that. So what we are doing is, okay, each time you read a batch, assume that 0.03 seconds of time has been taken for each of these in your samples. Like for each sample thing, this much time has been taken. So we are just like simulating that thing over here. Again, I've taken this thing from Code Basics, so just citing him. And here what you're doing is, for each of your epochs, for each sample in the data set, you are saying that 0.01 seconds of time delay is there. Now time it, what time it does is, time it basically calculates time, or how long does it take to perform that operation. So if you look over here, when I just did file dataset was basically this class which do this the construction, like basically simulates the entire system. It took 297 milliseconds. But when I said my machine, hey, do prefetch and then do it, it just took 237 milliseconds. So it saves time. Similarly, for caching, we already know what this mapping is doing, right? And everything. I'm just printing my dataset as a list. And here I'm saying that this is now time you sleep for it, like just showcasing that on dummy data. But again, when you ask it to time it on the file dataset thing, it takes 1.37 seconds for it to do. But when you tell it no dot cache, it just took 400 milliseconds. So again, we saw it saves a lot of time. And that was the idea of optimizing your data input. So like, it's not that data pre-processing and like building these pipelines is like a very easy task or something. Like, it does involve a lot of thinking, because like you need to think, is there a way I can be more efficient with my data? Is there a way that I can pass better things into my model, basically? Okay, so now we are just left with TensorBoard, which should take like no more than 4 minutes. I know I said 1 hour 10 minutes, and it's already 1 hour 10 minutes. So just TensorBoard, and we should be done. Uh, and we'll contrast. So the reason I'm showing you about searching it is to tell that the community support in TensorFlow is really good. They have really strong documentations, and if one would have wanted to learn TensorBoard on your own, what you would do is you would be like, okay, let me they had this thing here, get started with TensorBoard or TensorFlow. They have a Google Colab notebook here, so they give you a notebook to run and learn on your own. And what you're doing is basically just like read through these things, but you're loading the TensorBoard notebook extension. You're again importing your TensorFlow and datetime libraries. What this function is saying, as the name suggests, clear any logs from previous runs. If you ran this thing previously, clear logs. I want to get the new graphs. I want to visualize again how my data is. MNIST is a data set which basically contains handwritten digits and their labels. So like if somebody writes number 2, you should be able to predict number 2. So that's the data set for that. And then you use Keras. As I had said, tf.keras was the highest level of one of the highest levels of API hierarchy. So this, it only provides you with a model. And now what it is doing is, if you see, we had talked about that there were 5 epochs. So epoch 1 basically means dataset trained. Epoch 2 means dataset trained. Epoch 3 means dataset trained, and so on. So since we are running it for 5 epochs, this is just printing uh, the time, the loss, the accuracy, everything over here. But what we are trying to see is what is TensorBoard and how it's so good, like so important. And also PyTorch also supports TensorBoard. So if you're using a PyTorch, you can still access TensorBoard. But this is what my TensorBoard looks like. So if you see, you get your graphs of like epoch accuracy, like your accuracy is increasing, your loss is decreasing as it should. And like if you know that for your training part, the loss is decreasing, for your validation part, the loss is decreasing. And you might get to know that, oh, you're not overfitting, because overfitting basically means that the loss would increase after a while and some things. So like basically this is just to showcase that it's a good data visualization tool as well. Does anybody have any doubts with TensorBoard? Okay, then assuming nobody has any doubts with that, we are almost done. Just 3 more minutes and we'll be done with thing. So just to contrast what TensorFlow and PyTorch like differ. So this is just a graph showcasing that nobody knew about PyTorch pretty much then, and now it has pretty much filled this gap. And even based on how many research papers were implemented with TensorFlow and PyTorch, about 75% of them are implemented by PyTorch now. So does it mean that the world is shifting from TensorFlow to PyTorch, or what's happening? So technically, I won't say that one or the other is better. I think it's better for us to look at their similarities and maybe some of their key features to decide which one would make more sense for us to use in our respective projects or wherever we use these frameworks. Also, if you're planning to read about these two online, please make sure to read something which is recent, because you might find somewhere people saying TensorFlow is the best because it has the highest, like largest GitHub repository. It's number 10th repository now, but it's also because TensorFlow was started earlier. Somebody might say that TensorFlow has static graphs, PyTorch has dynamic graphs, therefore PyTorch is better. But now with TensorFlow 2.0, both of them have dynamic graphs. So basically, when I was looking to like write this data, I was looking at something, and there I saw that they mentioned this. But it's important to realize that we read recent publications. So I'm just going over these points. Both of them support Windows, Mac OS, Linux, Android. Both are written in C++, Python, CUDA. TensorFlow was written with some C too. Both offer CUDA support in parallel execution. Both support all kinds of neural network architectures. Both have pre-trained models. Both have automation. Both support Python, C++, and Julia as interface programming languages. TensorFlow also supports some other languages like Java, JavaScript, Swift, C, R, and Go. Both have auto differentiation uh, core functionality, and both of them have dynamic graphs. But some key features about each of them are, firstly, PyTorch is easier to learn. So if you're starting learning any of these, people usually recommend PyTorch because, as we know, PyTorch is pretty easy. Sorry, Python is like pretty easy to begin with, and similarly, PyTorch is pretty easy to begin with. It's said to be better for NLP and building rapid prototypes. It has a fast growth of resources, and as we saw with that chart, most research is done using it. However, for TensorFlow, as we saw, it has solid documentation and community support. The 2.x version of TensorFlow, it has most PyTorch features. It's production ready, which basically means that your models are uh, can be scaled better, and it has high level API for fast models as well. As we saw tf.keras, we also saw that in the code, the second code notebook. So that was like just a quick summary of what PyTorch and TensorFlow are, and that kind of wraps up the session today. So if you have any questions, I am here and you're free to ask.